Welcome to You Got Hope Chemistry. I'm Hope, and you're about to learn some chemistry. In today's lesson, we're going to continue our work with organic compounds, focusing on alkenes and alkynes. Now, we are going to look at naming and writing their formulas, drawing them, isomers, properties, as well as reactions at a very basic level. From our first lesson, you should remember that alkenes will have a carbon-carbon double bond and alkynes will have a carbon-carbon triple bond. So let's start with some naming. The basic rules from alkane naming still apply. We got to find the longest continuous chain. But the biggest difference is the -ene ending as well as the priority of the -ene. And what I mean by that is you need to number the double bond with the lowest possible number. This is even over naming a side group such as a methyl group and a ethyl group or propyl group have to be lower, may have to take a higher number in order to allow for the double bond to get the highest priority. So first of all, when I'm looking at my longest continuous chain, I can look here. This has 1, 2, 3, 4, 5 carbons. I could also go up. So I could go like this. And if I did this, it would be 1, 2, 3, 4, 5. Either way, we're going to get the exact same answer. So I'm just going to highlight the straight kind of chain section as my parent chain. And of course, we have 5 carbons here, 1, 2, 3, 4, 5. And then we have a methyl group up here. Now, when I want to start numbering this chain, again, my priority is to give the double bond the lowest possible number. So starting from the left, it could be 1, 2 methyl, or starting from the right, it could be 1, 2 ene. The ene has a higher priority. It must be numbered as low as possible because if I numbered it this way, this would be a 3 ene. 1, 2, 3 ene. Okay, so that's what we're going to do. We're going to number from the right. So this is 1, 2, 3, 4, 5. So starting with our prefix, which is our branch, this would be 4 methyl. 5 in organic chemistry is pent. And then I have to give the location of the double bond. So the double bond is always going to fall on 2 numbers, right? One carbon on one end and 1 carbon on the other. You pick the lower of the 2 numbers. So this would be 4 methyl pent dash 2 dash ene. This is the location of the double bond. It's the lower of the 2 numbers there. Now, before we continue on, let's do the actual formula for this compound. Now, a monoene, and in chain form, which this is a branch chain, is going to have the generic formula of CnH2n. The formation of this double bond requires each carbon to lose a hydrogen, so that's why it's not 2n plus 2. It's because this carbon had to lose a hydrogen, and this carbon had to lose a hydrogen in order to make that second bond. So let's read this. It says 4 methyl. Well, a methyl is 1 carbon. Pent is 5. So that's a total of 6. C6H2 times 6 is C6H12. So there's the generic formula for this compound. The actual compound is called 4-methyl pent 2-ene. The next one we're going to look at is an alkyne. And again, I really want to push the fact that the triple bond has to get the lowest possible number. So when I look at this, there's actually 3 different ways I could do the longest continuous chain. This would be 5. This would be 5. This would be 5. So I'm just going to keep kind of the flat straight line. And then if I was to number this, and it has to, the longest chain has to include that double or triple bond. If I went from the left, it would be 1, 2, 3 ine. And if I went from the right, it would be 1, 2 ine. So I got 2 branches here. And so these would be on the 1, 2, 3, 4, 5. It's on the 4th carbon. And so I would actually have to say 4, comma 4. Each branch has to have its own number. Now, because there's 2 of them, I have to say di. And because they're methyl groups, they're dimethyl. So there's my prefix, which are my branches, 4, 4, dimethyl. Again, this is a pent, so this would be pent. And then I have to give the location of the yne. So it is on the second carbon, so pent 2 yne. Then if we want to do our generic formula, if I have a chain monoyne, so there's 1 triple bond, and this is not in a cyclic style, then this is going to be a CnH2n minus 2. So each carbon here has to lose 2 hydrogens each. So that would be 2n plus 2 minus 2 minus 2, which gets us here. So the next thing I do, I'm going to count up how many carbons I have in my compound. So dimeth is 2, pent is 5, so that's a total of C7H14. And so that would be the formula for this compound. Now I'm going to give you a bit of a warning here. I want to draw this for you in terms of a line diagram because it looks funny, okay? You cannot bend around a triple bond, and so there's going to be a big flat section. So I'm actually going to start with carbon number 1 over here, and you're going to make a line. Okay. And then it would go, let's see, we'd have 1 carbon here, this is carbon 1. Carbon 2, that's carbon 2. Carbon 3. This is carbon 4. That's this one here. This is going to need to have branched out like that. It's going to look something like this. So I'm going to draw it one more time. I can start from the other end, and I could do a bend to the 4th carbon. Okay, but then I'm going to get a long continuous line. And I'm going to have a triple bond that looks like this. You can only make a linear shape around a triple bond. So again, this would be carbon 1, carbon 2, carbon 3, carbon 4, carbon 5. Carbon 4 has 2 methyl groups off of it, so I would have to go 1, 2. And so this would be the line diagram, and the only reason I bring it up is it looks quite weird compared to a structural diagram. The next thing we're going to look at is drawing a alkene, but I would like to start by figuring out the formula first. So here we go. We've got dimeth, so that's 2 carbons, pent, that's 5, and because it's ene, it's CnH2n. So I'm C7, 2 and 5 is 7, H, 2 times 7 is 14, so we're C7H14. Now, a structural diagram or structural formula for this is going to show all of the bonds. It's going to show all of the carbons and hydrogens, etc. So I'm going to start with my longest continuous chain, which is 5 carbons. That's my pent. Then I'm going to put my double bond in on the second carbon. So I'm going to put a double bond there. And then it says I have a methyl group on 2. So this is my second carbon. I'm going to put a methyl group here. And it says I have a methyl group on the third carbon down here. Okay, then what I would do is I'd mark off one of these. I'm not going to draw the hydrogens in terms of what they look like in here. I'm just going to assume every tick is a hydrogen. And I'm going to count things up. So before I do that, I got to make sure that every carbon has 4 bonds. So this first carbon here only has 2. It needs 2 more. The second carbon has 1, 2, 3, 4. It's full. This methyl group is full. Carbon number 3 has 1, 2, 3, 4. This methyl group has 4. This one needs 2 more. This one needs 2 more. And so what I'm going to do is I'm going to count up how many hydrogens I have, which there's a hydrogen at the end of each of these lines, just going around clockwise. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, and I'm good. Now a condensed structural is going to show the hydrogens collapsed into each carbon. So for instance, that first carbon has 3 hydrogens on it, so CH3. This carbon has no hydrogens on it, but it does have a methyl group coming off, CH3. Double bond. This one has no hydrogens coming off, but it has a methyl group, CH3. Then we have CH2, CH3. So there's our condensed structural diagram. Now our line diagram, I'm going to start with my 5. So I go 1, 2, 3, 4, 5. I'm going to make my double bond here. Now this doesn't need a flat section like a triple bond because this is going to be sp2 hybridization, which gives us a bond angle of 120 degrees, which is roughly what that looks like. Then I need to have a methyl group off of 2, and I need to have a methyl group off of 3. So that's how you would draw the diagram for this molecule. The next thing we're going to look at is figuring out isomers for alkenes and alkynes. And these ones are very commonly tested because they have some variety, but they don't get out of control too much. Especially the alkenes are very popular. Okay, so an isomer is when you have two compounds that look different, but they have the same number of carbons, the same number of hydrogens, and if there is a different element, the same number of that other element. So any isomer of a chain alkene, okay, so that's not in a ring, must obey a CnH2n formula. You could only have one double bond here. However, this is very new to you, and you need to remember this. CnH2n formula is also used for cycloalkanes. So if you're confused, this is what I mean. If I had a pent-2ene, that would have the same formula, which is, this is C5H10. That would have the same formula of a cyclopentane. This is C5H10. Now, we're not getting to cyclos till our next lesson, but a cyclic compound just is in a ring. So it's a triangle, a square, a pentagon, a hexagon, a heptagon, an octagon, something like that, although octagons are really strange and not very common. So these things both have the CnH2n formula. So a cycloane, there's no double bond here, so this would be a cycloane, or a chain-ene that has one double bond. Those would be isomers of one another. So that's what you're looking for, everybody. You're looking for a chain monoene or a cycloane that have the same number of carbons, and if this is true, you're gonna have a isomer. Now, alkynes have more possibilities, and so it gets more complicated. A chain monoine has this formula of CnH2n minus 2, which could be one triple bond or two double bonds or a cycloene. So there's a wide variety here of things that it could be. The cycloene could only have one double bond though. And then if you counted up all the number of carbons and they all had the same number of carbons, and all the things I was comparing were a cycloene or a diene or a ine, then they would be isomers of one another. So let me go over a kind of a quick outline of the possibilities of isomers here. We'll talk about C4 compounds, okay? So this here would be, C4H10. 2 times 4 plus 2 is 10. These are alkanes, essentially. And the only possibility for this would be a chain-ane. That's it. There's one possibility. So examples would be, just butane. That's butane. Or I could have 2-methylpropane. That's it. They're both chains. One's branched, one's unbranched. But there's kind of very little of what you can do when you are completely saturated, because these are saturated. Okay. Now, when you have a CnH2n formula, there are a couple of possibilities. Now, this would be C4H8. First of all, I could have a chain monoene. Okay, so one double bond. So I could have something like this. I could have but1ene, or I could have but2ene, or I could have a prop with a methyl group coming off of it. Okay, so those are all possibilities. I could also have a cycloane. Okay, so I could have something like cyclobutane or methyl cyclopropane. So I've color coded it for you there, but you can see already just by removing 2 hydrogens from the formula, the amount of examples I can make has escalated. It's more than doubled. Okay, and so that's what happens. It's almost exponential. The more hydrogens that are removed from our generic formula, we kind of get almost an exponential growth of what we can make with it. Okay, so this one would be C4, 2 times 4 is 8, minus 2 is 6, so C4H6, and this has essentially 3 possibilities. So 1, I could be a chain ine, monoine. Okay, so we could have, say, but1-ine. We could have but2-ine. Okay. We could have this as a chain diene. Sorry for the spelling there. So di means 2, ene means double bond. So I could have something like this, but1,3-diene. That's a possibility. And 3, I could have a cycloene. So I could have cyclobutene, or I'm not sure if this exists in reality, but this is cyclopropene with a methyl group on there. And I could also have a cyclopropene with a methyl group there. So again, there's lots of different possibilities. The less hydrogens you have, the more manipulations you can really do. In terms of chemical and physical properties, they have very similar properties to alkanes. So again, they're non-polar, so they're going to have London dispersion forces only in terms of intermolecular forces. So their solubility in water or other polar compounds is essentially nothing. Solubility with other non-polar compounds is extremely high. And the only thing that's a little bit weird is the melting points and boiling points. So generally when we're talking about London dispersion forces, the bigger the molecule is, the higher its boiling point is. So essentially the more electrons you have, the higher your boiling point is going to be. So technically the way this probably should look is alkynes have the least number of atoms. They should have the lowest boiling point. And then it should go enes, anes. But it actually, alkynes have the highest boiling point out of them because of that flat section around the triple bond. Now this is a nuance that is very unlikely to probably be tested at our level, but it's something I would mention. So for instance, if I was to do something like C3H6, so propene, this would have the lowest boiling point compared to an alkane. Okay, so C3H8 of the same number of carbons. So because C3H8 has 2 more hydrogens, has 2 more protons, it has 2 more electrons, it's got a higher amount of London dispersion force. Now, this is the one that falls outside of the pattern. Really, you would think alkynes, which would be, this would be C3H4, would be the lowest, but it isn't. It's actually the highest out of the 3. And this is due to the fact we have this very flat section. When I was drawing that, it would look like this. Okay, that would be propyne. These flat sections where there's no bend around this carbon is going to allow those molecules to stack on each other really well and allow the electron clouds to shift and causing a polarization effect. The last thing we're going to look at is what kind of reactions do alkenes and alkynes undergo. Now, all hydrocarbons can undergo combustion, and I talked about that in detail in the previous lesson, and we're not going to cover that here. Combustion is something you cover in chemistry from a very early time. The big one that we're going to talk about here is addition. It is pretty much exclusive to enes and ynes. In an addition reaction, what you're doing is enes and small molecules will react with one another, and the small molecule will become part of the larger molecule by adding into the double bond, effectively converting the double bond into a single bond. We're adding in something small. And when I say small molecules, I mean a lot of the diatomics, so H2, Cl2, Br2, I2, the hydrohalogens, HCl, HBr, HI, oh, I can't forget about F2, HF, and water. And I break water into H and OH because that's kind of how it adds into a double bond. Okay, so essentially the entire small molecule, again, I'm going to call these small molecules, add into the double bond. The key part is one atom goes to one carbon in the double bond and one atom goes to the other carbon in the double bond. They cannot go to the same carbon. Now, in all addition reactions, generally there are two reactants but only one product. There is a little bit of an asterisk here, except if there are isomers. So if there's isomers being produced, then there is more than one product. We're going to stick to something very simple where there really is only one product. Now, for the purpose of our course, we say that benzene does not undergo addition reactions. And remember, that's because benzene doesn't have double bonds. It has 6 1 1/2 bonds. Now, is it possible to add hydrogen into a benzene and turn it into a cyclohexane? It is. And is it done? Yes, it is done. But again, for the purpose of our course, we really don't look at benzene undergoing addition reactions at all. Benzene almost exclusively does something called substitution reactions, but of course you can burn it as well. So let's do a couple fairly straightforward, simple questions. I'm going to do one with a structural formula and then one with a line diagram. Okay, so we're going to stick with something nice and simple. Propene is going to react with a chlorine molecule. So here's the propene, and I'm going to draw the double bond on the end. So this is what it would look like. And I will actually draw the hydrogens into this picture. So again, prop means 3, so C3. Ene means times 2, H6. I got 3 carbons. I have 6 hydrogens. This is, one too many there. Okay, I have 6 hydrogens, and there we go. So I'm going to draw chlorine with 2 different colors. So I'm going to say plus Cl, Cl. And the reason for that is I want to kind of show you that when this chlorine double adds into the double bond, one goes to one carbon and one goes to the other. You would never have this hydrogen break its bond, move over here, and then have both chlorines on this. The only bond that's being broken during an addition reaction is one of these bonds here. It's specifically called a pi bond. It's the second bond in a double bond. It's being broken, which allows each carbon to pick up one more element. Okay, and so that's what would happen. This chlorine would go here. This chlorine would go there, and you would produce CHHH, CH. I'm going to put the Cl here. CH, and Cl. Now, if you're wondering, does it matter if these Cl's both go on the bottom or top and bottom or whatever? This is a two-dimensional piece of paper. This is not what it looks like. Each of these carbons has a tetrahedral shape around it. The atoms can rotate around this single bond. It really doesn't matter where I put the chlorines, other than this chlorine could either be, here or here. This chlorine could be here, here, or here. It does not matter. When you name it, it's the same thing no matter what. Now, I know we have not named halides, but I'm just going to bring it in now, and we'll just name this one. So a halide would have a prefix. So I have a 1, 2. This is carbon 1, carbon 2. Di, because there's 2 chlorines, dichloro. And because there's 3 carbons, dichloropro. And now they're all single bonds. It's just propane. And so that's how we would name this compound. So let's do one more, but we'll do it with a different small molecule, and we'll do it with a line diagram. So for instance, sorry, I meant to make this propene. Okay, propene reacts with water. So I'm going to draw propene like this. Here's my double bond. It's going to react with water, and I'm going to do something similar. We're going to go H, but I'm going to make it look like this, HOH. Now, normally in a question, it would be written as H2O, but this is to give you a visualization of what would happen. Okay. Now, technically, the hydrogen can go to either of 2 of the carbons, and the hydroxyl could go to either 2 of the carbons, and we will get 2 different isomers coming out. One will happen in a higher amount, but our level, we don't really need to know what those would be. So there's really 2 isomers coming out of here. Okay, we could have the hydroxyl group add to the very end. So I could have the OH group here. And just so you can visualize it, I've got a carbon here, carbon here, carbon here. The OH is there. That means that this hydrogen would then be added there. And so this hydrogen would be there. Okay, so that's a better way of visualizing it. Then the other option is it could look like this, and it could have the OH group off the middle. I do believe this would happen in a higher amount. Again, we'd have carbon here, here, and here. But in this case, the hydrogen would be on the end. And so we have essentially 2 different isomers. This first one would be called propan-ol, or propan-1-ol. And this one would be called propan-2-ol. So that's just a very brief overview of 5 different things about alkenes and alkynes, how to name them, how to write their formulas, how to draw them, what are their properties, what are their isomers, and how do they react. I hope you have enjoyed this lesson of You Got Hope Chemistry. See you next time.